A key to low-rank approximation is that we know or assume that there is some structure within the data that we can take advantage of. PCA assumes some sort of statistical distribution of your data. KSVD sometimes can be thought of as more shape-based. It assumes that you have a finite number of atoms that are used to create the data that you've observed. ARMA modeling makes an assumption of the data based on how it was produced. And ARMA stands for autoregressive moving average. We're going to start by making the assumption that what we're observing is actually the impulse response of a system. We will generalize this a little bit later, but this is a really good place to start. And when I say we'll generalize it later, we'll show how it applies to something else. We really don't have to do anything much different. So we'll assume that we have some observation, x of n is approximately equal to an impulse response, h of n. Now we want x of n from our model to be as close as possible to h of n. So whenever we're trying to get something close, let's define our metric. And in this case, I'm going to call this E prime, and you'll see why in just a minute, is equal to x of n minus h of n. Now, if we have a linear system, we can assume that the Z transform of an impulse response can be written as the rational transfer function, oops, it's AP, where B is the feed forward part of the filter and A represents the feedback portion of the filter, or the IIR portion. Q represents the order of the numerator, and P represents the order of the denominator, or the feedback portion of the filter. All right, there are several ways to approach this. Ideally, we would like E of Z to go to 0. So let's go ahead and put that. Ideally, E prime of n equals 0. And so we set that to equal to 0 and solve for our A coefficients and B coefficients. This is called Padé method. And there are some issues with it. It's, in general, really, really hard to do. Just to give you an example, we know that if you have an IIR system, that could be represented entirely as an infinitely long feed-forward system. And eventually, of course, it will damp down to 0 if it's a stable system. So we can then round that and have it be a finite number of feed-forward coefficients. So if, for example, the filter died off exponentially like so, well, this could have a very simple, maybe 1 or 2 coefficient feedback filter, or it could be a longer FIR filter that approximates that arbitrarily well. So which do you choose? You can start to see the ambiguity with the Padé method. It's not very stable in terms of an approach to solving these things. So we're not going to use this. Instead, we're going to work on something called Prony's method. So Prony's method gets around this ambiguity by coming up with perhaps a non-ideal way of solving the problem, and that is this. We're going to define a new error function. You wondered why I defined our prior error as e prime of z. It's because we're defining a new one. E of z is equal to the denominator polynomial ap of z times e prime of z. So that's essentially now a of z, our feedback polynomial. But now we're multiplying by it instead of dividing, so that turns the IIR filter defined by our a coefficients into an FIR filter. And then we subtract BQ of z. And we can see that if e prime of z was equal to 0, this will be equal to 0 as well. So it's a reasonable approach to take. The problem comes when we don't quite make it to 0. If we were working on e prime, we would it would behave well. If we're working with e of 0, now instead we have effectively a weighted error, and it's weighted by the pole positions in a of z. So let's figure out how to use this then. The first thing we're going to do is, since this is an impulse response, we're going to assume that x of n is equal to 0 for n less than 0. So this next part is kind of important in understanding how to frame this and how to work this. We can note that h of n, which is our impulse response, can be written in several different ways. One, it's an impulse response. We have the impulse as an input. We can convolve that with the feedback portion of the filter, followed by a convolution with the feed forward portion of the filter. Here, let's define HA of n to be the inverse Z transform of 1 over A P of Z, and HB will be likewise defined in terms of BQ of Z. So normally when we write filters, we don't hang around, we don't keep these the A's and the B's around explicitly, but this matters because we can also rewrite this as, because it's a linear system, we can change the order of operations. HB convolved with HA. So the entire system is infinitely long for everything but a trivial feedback filter. But this portion right here is only Q samples long. So we put an impulse in, and out of the FIR portion we get Q samples. Those samples are each filtered by HA, and but after Q time steps, there's no longer an input into HA, and that's a key. And so that allows us to write E of n in this manner. We will have, it's going to be equal to x of n and I'll explain this in just a moment. Goes 1 to p APL X n minus L minus BQ of n. And that's for n equals 0 to q. Then, after that, we no longer have this b. It's going to just disappear. And so we're going to have x of n plus L equals 1 to P A P L n greater than q. Okay, a few things here. First, where does this come? This comes from A0, and nearly every system is defined as equal to 1. And if it's not, we can always normalize it and put the normalizing gain into the numerator of our system and have it show up with the FIR part. And this system here represents that highlighted portion. And this shows up here. But since we had an impulse as our input, the length of BQ of n is only q plus 1 samples long. And just to keep track of things, this is the same as HB of n. Okay, well, what we're going to do first, because we have to solve for the B's and the A's, and that can be kind of tricky, but if we focus on this part, there are no B's to worry about. So let's write this formally. We will minimize the sum from n equals q plus 1 to infinity of en squared with respect to our A coefficients. Let's write that as a vector. And we'll do this by taking the derivative with respect to the A coefficients. So, if we take the derivative of this function with respect to A star, P of k. Now, why are we doing this with A star? It turns out that I've done what I sometimes do in this class and jump back and forth between assuming everything's real and assuming that it could be complex. It's probably real, but I've gone ahead and shown you the complex solution here. When we want to minimize a magnitude, we're really minimizing an A times A star. And if we take the derivative of the A star, this is the appropriate way to proceed. And so we get now the sum of n equals q plus 1 to infinity of E of n x star n minus k equal to 0. Actually, I guess I skipped a step. Let's put this in just to make it clear. This would be E star n with respect to A star P K for K equals 1 to P, and that gives us E of n x star n minus k equals 0, once again for this same range of k. Expanding out E over the range of interest here, so once again we don't have our B coefficients anymore. We get A P L x n minus L times x star of n minus k. While using that famous old trick of reversing the order of sums or summation in any DSP proof, we get n equals q plus 1 to infinity. Actually, this goes outside. L equals 1 to P of AP of L times x n minus L x star n minus k, and we can put the x term over on the other side, giving us the sum q plus 1 to infinity n minus k. Well, we can define this, something that we've seen before. This would be R x k comma L, and it's equal to that sum, which I won't repeat right here. And then this will be R x 1 comma or 0 comma k. Let's put it as k comma 0. Okay. Once again, we've run across this before. This is not the actual autocorrelation function. We sometimes call this a deterministic autocorrelation. And there are several differences. One, it's not an expectation, it's a sum. The other difference is nothing is normalized. I mean, normally we would have like a 1 over n out front, but since it shows up on both sides, they just cancel out, and we end up just using this term here. So the equation from the previous page, it's actually a system of equations, because we're solving for all these different values of A, or AP1 through APP. It can be written as a matrix equation. Like this. Remember, we had this negative sign that we want to carry through. Since it's not, I didn't write it in the matrix itself, it might be easy to miss. Okay, if we define this now as our deterministic autocorrelation matrix Rx, this would be a vector A, P, and this will be a vector R, X. We get our system of equations with an obvious solution of AP is equal to Rx inverse times negative Rx. Well, to come up with our values of Rx, we had sums, you may recall, that were infinite, which generally slows down computation on most computers. And so we will instead write things just a little bit differently. We can actually choose however many samples that we want to do this. We're going to need to have at least p samples of data in order to make sure that things work out. And I'll show why, I guess, logically in just a minute. Let's let, first we'll draw a nice red circle around that, and then we'll come here and define this x vector, data vector, very similar to what we did with PCA. So we define a vector x that has this type of structure. Then Rx is just equal to x Hermitian times x. And our little Rx is just equal to x Hermitian times x q plus 1, just a single vector, where I guess we should define xq plus 1. It's kind of what you might expect. It's a data vector like that. Okay. In practice, we can choose however many we want. Choose as many samples as possible. But not less than p. Okay, so why is it can't be less than p? It's because this is formed as an outer product. And so the rank of that outer product is going to be the minimum rank of x of q. And if x of q has too few samples, for example, if we only had 2 rows, then that rank would just be 2. And then it wouldn't be invertible, and we would have a hard time solving things. But we're going to talk more about how to actually efficiently solve these problems in the next lecture. But let's just finish the last little bit. We now have our A coefficients circled here in red and highlighted. We now need to get the B coefficients to complete our problem. So to find the BQ coefficients, let's go back and look at this system, or not system, but the equation where we had E of n was equal to AP of n convolved with x of n minus bq of n. And this is the equation highlighted here in yellow and blue. I just went ahead and wrote out the convolution in the highlight. Here I just expressed it as a convolution to make it easier. And then we set this to 0 for n equals 0 up to q. Well, that just gives us bq of n is equal to, amazingly, ap of n convolved with x of n. Oh, that's it. Okay, let's spend just a moment and figure out why this works and what's going on. Obviously it works because that's how the math comes out, but you can get another bit of intuition by looking at it this way. If we have delta of n going into some filter with feed forward and feedback portions, giving us h of n, this is identical to delta of n actually, we don't need to cover that. Let's just do it this way. So h of z is now equal to b of z over a of z. And if a hat, our estimate here, is equal or approximately equal to a of z, then filtering our signal with a of z, then h of z times a hat of z approximately equals b of z, because the a and a hat would approximately cancel. So that's it. Effectively, we have to wait till we aren't excited, till there's no input, and the FIR portion has died away. And once that's happened, we estimate our signal autocorrelation values, and we can solve for our A's. Once we have our A's, we can get our B's and proceed like that. Now, before we go into the actual numeric method of solving this, I want to talk about how this is done in practice. Often, you know that there's some excitation. Maybe it's a periodic excitation. Speech is a really good example. The excitation comes when your glottis opens, air rushes into your vocal tract, and bounces around and comes out. And so this happens over and over at your pitch rate. So when the glottis is closed, there's no excitation, and your vocal tract is primarily an all-pole model. And so we just wait till the glottis is closed, and we can come up with our A coefficients. However, how do we know when the glottis is closed? So we do this. We hope we can find the A coefficients, but we actually may have a problem. If we're observing our speech when the glottis is open, we won't get accurate results. However, we can take the results that we get, estimate the B coefficients. We can think of the glottis as the FIR response as it opens slowly and closes due to an impulse. So we can estimate approximately, using this method, when the glottis is open and when it's closed. Now we take the period where we are pretty sure it's closed and we re-estimate our A's. We might do this once or twice and get a really good idea of what our feedback coefficients are. When we have these coefficients for speech, an order of 10 is commonly used. When we have these 10 coefficients, we can now compress our signal substantially, because we just need to send a compressed excitation signal and then a compressed copy of the feedback coefficients. And that's what's done in speech coders.